Hi everyone, welcome to Sri Chaitanya IIT Academy. I'm here to take you to the paper analysis of JEE Mains 2021. I tell you two things. First, these questions are from the memory of our students, so there can be an error or two. Second, this will be immensely helpful for the upcoming aspirants. So question number one, what is the reason for formation of meta product of the following reaction? So now we have an aniline here as a substrate, and we see the reagents. These reagents points us to nitration, right? But then why we have a meta product in spite of the fact that there is a lone pair on the top of nitrogen atom? Reason is that in presence of H plus, the lone pair sitting at the top of the nitrogen atom gets protonated, and as a result, we have any selenium ion. This is the fellow. Now, this particular group, which is attached to the ring, is highly deactivating, and therefore we are having a meta product in a significant amount. So the most appropriate answer seems number 4. In the next question, what we have is that we are to find this pink color because of the addition of a particular reagent, P. Now, what is P? Now, whenever you have a pink color, the first thing that should come into your mind is about phenolphthalein because it's very popular in the entire course. Now, if you can recall the structure of phenolphthalein, half of your work is done. So this is basically your phenolphthalein, which I'm trying to draw it here. So this is your phenolphthalein. Now, if we can arrive at something similar to this particular structure, we can get the pink color. Now, what is the options given to you if you analyze? We have a benzene ring and certain groups are attached to it. Now, what about these groups? OH. OH is an activating group, right? So it's ortho para directing. It will increase the electron density at ortho and para position. But the attack from the ortho position is less likely because of the steric factor. But the attack from the para position is most likely due to lesser steric hindrance. Now, if we observe the substrate and the reagent, the H plus will come out from the medium, will get protonated at the lone pairs of oxygen atom. And as this protonation occurs, the oxygen atom bears a formal charge of +1, which it doesn't like. So in order to get rid of that, it will shift the adjacent bond pair onto itself, resulting into the formation of what we called something similar to acylium ion. Now, this is very much similar to Friedel-Crafts acylation. Now, if you can understand the effect of phenol, what is going to have, the resonance will increase the electron density at the para position, and from this para position, it will attack at this particular carbon. And as a result, the charge of the carbon atom will be gone. So what we have? We have this particular product. This particular oxygen will bear a formal charge of +1. Now, since the medium is acidic, another protonation can occur here. And as a result of that, this oxygen atom will bear some positive charge which it doesn't like, and therefore it will attract the loosely held pi electrons onto itself to get rid of that positive charge. As a result, we will arrive at something like this. Now these two rings, initially they were aromatic. Now the aromaticity has lost, which is not favorable. The aromaticity will be regained, and there will be a loss of water molecule from here as well. And if you try to understand, you are going to get something similar to this particular structure, which is my phenolphthalein. So what is the key here is to understand the attack is going to happen from the para position with respect to OH group of the benzene ring. And in these options, option 2, option 3, option 4, the para position is occupied. So we are left with only option 1. Next is very simple and straightforward. What is the reason for an alpha helix structure of protein? Basically, we're talking here about the secondary proteins. So what happens is that proteins are nothing but polypeptides. So you have a group CO, and at the same time, you'll be having a group NH. Now these hydrogen and this oxygen will have some interaction, and this interaction is nothing but a hydrogen bonding. And because of this bonding, we arrived at such a structure. So the first answer is correct. The gas evolved due to anaerobic degradation of vegetation. Now this is very straightforward, informative. The gas is CH4, which is a greenhouse gas as well as a cancer-causing agent. So we can see the answer 1 seems appropriate. Now 5, here we have a match the following. Left-hand side, we have monomers. And in the right-hand side, we have polymers. Now, first option, that is caprolactam, is something like this. Now, this particular structure or this particular monomer, when heated above 500 Kelvin, approximately 533 Kelvin, it gets converted into this particular polymer, which is referred to as nylon 6. So there's a spelling error here, please mind it. The next one is acrylonitrile. So what is the trick here? N stands for nitrile, and also we have an N here. So it is basically a monomer of buna N. So this buna N is a polymer of two things. One is 1,3-butadiene and acrylonitrile. So 2 should match with B. 2 should match with B. Okay. So here, if we eliminate, go by elimination, we straight away eliminate 1 and 2 because 1 is definitely C. So we have third or fourth option. And then 2 matches with B. And when we arrive at this particular area, so my answer is fixed. That is third is my correct answer. Let's look at 3 and 4. 3 is 2-chlorobutadiene. So 2-chlorobutadiene will give you neoprene. So neoprene is an addition. Neoprene is an addition polymer of 2-chlorobutadiene. So this is when it will undergo addition polymerization, it will be something like this, which is nothing but neoprene. Again, the last option, 2-methyl butadiene, buta-1,3-diene. This is a monomer of natural rubber. So this is pretty much straightforward. So answer here is third one. So all this kind of question, you should go by elimination technique because partial knowledge can also lead to a correct answer. Next here we have alcohol as a substrate and we have an acid. So first step we will do is protonation. So as a result of protonation, this oxygen will bear a partial formal charge of +1 and turn into a good leaving group. What does good leaving groups do? They always leave. So as this water molecule leaves out, sorry, there isn't a ring. So there is a formation of a carbocation. Now, of course, we know about carbocation rearrangement. This can get rearranged, and we can obtain a 3-degree carbocation, which is more stable, via a hydride shift. Now, what will happen? Finally, this Cl- will attack here. And since it is a planar species, attack from top side and bottom side both are possible. We are going to obtain something like this, and I see option 1 is correct. Next, here we have an electrophilic addition reaction of alkene. So again, we have a strong acid here, which is going to furnish H+. The pi electrons will get protonated. As a result, we are going to obtain a carbocation. Now, this carbocation can undergo rearrangement to a more stable carbocation via methyl shift. And we get a 3-degree carbocation. This I minus, which is waiting in the solution to attack, will attack at this positive center, and we are going to arrive at this particular product, which matches to option number 3. Here we see Mg and ether, so everything points towards Grignard. So a little bit heat is also required, but we will assume it. So what is going to happen in the first step is a formation of a Grignard. So this Mg is going to give its 2 electron, which is going to attack at the positive center, which is the carbon attached to bromine, and bromine will be kicked out. As a result, a carbanion will get established here. Magnesium is still there with a +2, and Br is with a minus. Now, since a leaving group is already present inside the molecule, this carbanion will attack in an intramolecular style to arrive at a cyclic compound, kicking this other bromine out. So we have this particular compound as a product. So I see option 2 is correct. In the next question, we have this particular substrate, and then we have this particular reagent. Now, what is that reagent? This is Bayer's reagent. What does it do? Cis hydroxylation. So that means what? 2OH will get attached on either carbon, but from the same side. So that means this CH3 group is now at the bottom. Now this is my A. Now here I am giving CrO3, which is my Jones reagent. This is a strong oxidizing agent, so it will oxidize the alcohol. But then which alcohol? Only those alcohols can be oxidized which have at least one hydrogen attached to the alpha carbon. This particular carbon doesn't have any hydrogen, so it cannot be oxidized. But this one has. How many hydrogen it has? 1. So it can be oxidized once, leading to a ketone at that particular position. The question is not talking about stereochemistry, but I'm taking care of that as well. Here, I'm going to obtain a ketone. So if I look at my options clearly, option number 1 satisfies. In the 10th question, what has been asked is that they are looking for selective oxidizing agents. That means this particular alkane, when it is oxidized vigorously, it can be oxidized vigorously, I'm saying, I will end up getting a carboxylic acid. But then I need to stop at aldehyde because the right-hand side is an aldehyde. So this particular reagent, that is molybdenum oxide MO2O3, is a selective oxidizing agent that will oxidize alkane into aldehydes, into corresponding aldehydes. Next question is about diazonium. The first reagent points that we have a aniline. So what does this first reagent will do? We are going to get a diazonium. We're going to get a diazonium. This is it. Now we have a second reagent that is KCN. The Cn minus is going to attack and kick out N2 gas, leading to a formation of Cn here. Along with KCl, of course, aqueous present in the medium. Now, what we have is the other set of reagent, that is SnCl2 and HCl. This is nothing but Stefan's reduction. Now, this set of reagent will do what? Will convert the cyanide group into an aldehyde. So here we are going to obtain an aldehyde. Now let's check. So option A, that means the A part should be a cyanide. So 1 or 3 seems correct. So I'm eliminating 2 and 4. And what is B? B should be an aldehyde. So 3 is the correct answer. In the next set of questions, we have isostructural. Isostructural refers to being same structure. So if I talk about TiCl4 and SiCl4, of course, they are having the same structure, sp3, tetrahedral geometry. Here also, SiCl4 is the same. This is sp3 tetrahedral, right? So that means the structures are same. At the same time, we have this option B, which we see like this. So they are also having the same structure, that is tetrahedral. Now, what is the key thing that you need to understand? That there are some similarities in group 4 and group 14, and at the same time, group 6 and group 16. So I'm talking about group 6, that means I'm talking about chromium. Group 16, I'm talking about sulfur. So they are having some similarities, right? Sulfur and chromium. In a similar manner, silicon and Ti is also having some similarities. So with this, I conclude option 1 to be correct. Next one is from metallurgy. They are asking which of the ores are concentrated by cyanide of first group. So remember this thing, when ZnS is present with PbS, we use cyanide solution, either KCN or NaCN, to suppress the floating ability of one and concentrate the other. So that is the concept of activation and depressant. So what happens is that if they are present together, so we'll apply a cyanide solution. Since zinc is a D block metal, it will have a greater tendency to form complex, and it forms a complex ZnCN4 2 minus, which is a soluble complex, and as a result it goes into the solution, remaining PbS afloat. So now PbS can be concentrated and separated, and after that what we do here, we recover this zinc by introducing something like copper, and then the zinc is again separated, right? So here the answer is splerite, because splerite means ZnS. Malachite is basic copper carbonate, CuCO3 dot CuOH2. Calamine is ZnCO3. Siderite is FeCO3. So the answer here is 1. Next, we have colorless cupric metaborate is converted to a cuprous metaborate in luminous flame. Now, see, 2 statements are given here. The first statement is incorrect. I'm considering oxidizing flame. See, if nothing is mentioned, we should talk about oxidizing flame. Now, I know a fact that cupric metaborate is blue in cold condition under an oxidizing flame, and it is green when it is hot under an oxidizing flame. But if I talk about reducing flame, then cupric metaborate is opaque and colorless. But since nothing is mentioned, I will go by oxidizing flame. So in oxidizing flame, cupric metaborate is colored. Okay, in cold condition it is blue, while in hot it is green. So statement 1 is incorrect. Now statement 2, cuprous metaborate is formed by reacting copper sulfate. See copper sulfate, that means copper is present in +2. And in cuprous metaborate, copper is present in +1, right? So how you are obtaining +1? When this +2, you are reacting with boric anhydride. That means boric anhydride must act as a reducing agent so as to obtain +1. Now, do you know about boric anhydride? Yes, it is B2O3 and it is not a reducing agent. So it is not going to reduce this particular +2 into +1. So statement 2 is also incorrect. That means my answer is number 3. Next question, here we need to look about H2O2. In the first reaction, look at H2O2. It is reacting with I2 and I2 is reduced from 0. It is being reduced to -1. So here H2O2 is acting like a reducing agent. In the reaction 2, we see that H2O2 is reacting with HOCl, and finally what is happening, that oxygen from HOCl is removed. Now removal of oxygen is called reduction. Here also H2O2 is acting like a reducing agent. So option 2 seems appropriate. Now this is a straightforward, easy question for you. Now generally metals, they are asking about the metals and they are asking reduction potential. So reduction potential for the metals are expected to be negative because they are electropositive. But we know about copper. The standard reduction potential of copper is plus 0.34 volts. 0.34, let me correct it, 0.34 volts. So it is a positive value and we should remember it. Next question, here we are having aluminium reaction with alkali. See, we need to know about the amphoteric nature of aluminium. This is going to react with acid as well as base. So here it is reacting with a base, so it is displaying its acidic behavior. So what you need to know, this NaOH will corrode this metal, and as a result, Al plus 3 will come out in the solution, which will be complexed by 4 OH negative ions. Why? Because Al plus 3 is very small. It cannot go to a coordination number of 6. 4 coordination number seems cool because Al plus 3 is very small. Now this complex is going to have a net charge of -1, and therefore Na plus will be associated with it. So as a result, what is X? X is nothing but Na, and this complex, how many OH? 4 OH. Now this particular thing, when subjected to CO2, you are going to get, the aluminium is going to get converted into Al2O3, that is hydrated aluminium oxide. This can be also written as some form of AlOH3. Now, why it happens? Aluminium is amphoteric, I told you. So here, this is the hydroxide of it, and this is the acidic oxide. So this hydroxide acts as a base, and this one acts as a acid. So as a result, we're going to get this particular compound, and I see option 1 seems appropriate. Now, next we have a question from Frenlich adsorption isotherm. Every year this question has been asked in some form or the other. Make sure you do it before the day of the exam. So what is adsorption taken per unit mass of the adsorbent? It is equal to some K times, which is a constant, pressure applied raised to power n. Now you take log on both sides, what you're going to get? You're going to get this. Now clearly 1 upon n is the slope, right? And n can take values from 0 to 1 in intermediate pressures. 0 and 1 is not included when you're talking about intermediate pressure. When the pressure is extremely low, then it's a different issue. When it's extremely high, it's a different issue. So option 1 seems appropriate. Next, we have a gunmetal. This is a very factual type of a question. It's an alloy of copper with zinc, tin, or lead. N-lead, I should say N-lead. I should say N-lead. This is N, right? Let me rub it once for you. Zinc, tin, lead, right? I don't see a lead here, but option 1 seems appropriate. Now this is, they're talking about here the trend of ionization potential. So you should be aware of the factors on which it depends. Factor number 1 is Z effective. This is the first factor. And factor number 2 is electronic configuration. Now, when we take care of only factor 1, that means from left to right, Z effective increases, and therefore ionization potential or ionization energy should also increase. But then we have only considered one factor. This factor is still left out. Now, how to take into that? You have to look for stable configurations. Wherever we are having stable configuration, it will be difficult to take out that electron, which means additional energy will be required. Now, if I talk about stable configuration, this entire family is going to have a stable configuration of a fully filled subshell. And this particular family also enjoys a stable configuration of half-filled subshell. So in these two cases, you will be required a greater ionization potential than expected. And as a result, it will come ahead of the next immediate neighbor. So it will come here and it will also be placed here. The final order, you'll be getting something similar to this. So this is the order of ionization potential. Here at equilibrium, this is the equilibrium they're talking about. And surprisingly, it is homogeneous, gaseous, so there's no problem. At equilibrium, they're talking moles of Cl2 is equal to moles of Cl. So let us assume the moles to be some N. This is the moles at equilibrium. Since the moles are equal, their pressure also has to be equal. Their partial pressure values has to be equal. So let us assume some P and P. And if the total pressure is given as 1, so what will be the value of P? P will be equal to half. Now, how to write down Kp? For this particular equilibrium, partial pressure of Cl gas raised to power 2 divided by partial pressure of Cl2 gas raised to power 1. Now, since both the values are equal, we are left with only P, which is equal to half. That means 0.5, 5 into 10 to the power minus 1. When we compare with this thing, what is x? X is equal to 5. Next is a disproportionation reaction. Here, non-metals usually disproportionate in alkali. That has been the key point of the question. But again, we need to focus on balancing. How it is disproportionation? Sulfur, it's 0 in the left-hand side. In the right-hand side, at two different places, we have a -2 here, and here we have a +2. So definitely it's a disproportionation. So when I talk about oxidation, let me segregate it. So this is S8 changing into S2O3, 2 minus. And what is reduction? This part is my reduction, S8 changing into S minus 2. Now, what I do, let me balance them. I need a 4 here. If I put a 4, then means 12H2O. I'll require 24H plus. Since it is happening in basic medium, I'll have to take care of that as well. So I'm adding 24 OH minus on both sides. Now, if you see in the right hand side, there's an excess of electrons. So I need to add 16. I need to add excess of positive charges there. So I need to add 16 electrons in the right hand side. The reduction part, if we focus, we need a 8 here. And once that 8 is done, right hand side is having excess of electrons. So I need to add 16 electrons here. Now, the number of electrons is coming out to be same, which means we are lucky. So we simply add them up. So when we add them up, we get 2 times of S8. And in the right hand side, what I'm getting is that 8 times of S minus 2. Forget about others because I'm not worried about others. Only focus on these two. Now, if you simplify, 2 goes and this will turn out to be 4. So the stoichiometric coefficient C here, it is 4. So C is equal to 4. Next, we have a calculation of time for a first order process. So how to calculate time? It's very easy. So 1 upon K, we write down the solution of that differential equation. If we write it in terms of log, that is 2.303 log of, we take 100 initially, and when 40 gone, we are left with only 60. So that means this subtraction part is 40. So now if we put the values here, what is K? 3.3 into 10 to the power minus 4. This is 2.303. And this comes out to be log 10 by 6. Now log 10 is 1 and log 6 is around 0.78. So we'll be having that part simplified to something like 0.22. When we multiply, we get something around 1535 seconds. The multiplication part is not my part, but this is here chemistry ends and rest is your calculation. Next, we have to find out the delta G. Okay, delta G can be written as minus RT ln K. Now, minus R, we know we have to write it in terms of R. So what is T? T is 300. And what is K? K is your, let me convert it into log 2. So it will be like, okay, let me in that particular manner only, ln of 10 to the power 2. So I am left with minus R 300 into 2. ln 2 is nothing but 2.3. So it becomes minus 1380 R. So the value of X here, it is 1380. Next here we have a series of complexation processes, but they are asking the reverse of it. That means they are asking the dissociation constant of this particular fellow. That means this particular fellow is this. So we are going all the way from this particular thing to this particular species, right? So that means everything now needs to get back in a reverse manner. So if I write down these reverse reactions and if I sum them up, so what will I get? What will I get? I'll get this. I'm going to get this. Now, what will be the equilibrium constant of this? Remember, when a reaction or equilibrium process is reversed, the equilibrium constant becomes the reciprocal of the earlier. And when reactions are added, the equilibrium constant gets simply multiplied. So here, first they will be reciprocated and then they will be multiplied. K1 multiplied by K2 multiplied by K3, and finally we'll have K4, which will sum up to something like 1.26 into 10 raised to power minus 12. When you evaluate, that means X is equal to 1.26. Next, we have a question from colligative properties. Can I consider this particular acid simply as HA? So I'm writing the equilibrium established inside that container, H plus A minus. Now, if at 0, this is N naught, till the establishment of equilibrium, some moles are going to get dissociated, right? And not alpha. This one will also become N naught alpha, and this one will also become N naught alpha. So from here, we get the feeling that N naught 1 plus alpha divided by N naught is nothing but Van 't Hoff factor, which simplifies to 1 plus alpha. Now delta T F is equal to I times of Kf times of molality. Now this I is nothing but 1 plus alpha, Kf is 1.86, and what is molality? We need to find out. For that, something is missing in the question, I see. Okay, I remember for some reason that this is 9.45 grams given in the question. As I told you, it's totally based on memory. So I'm taking 9.4 gram divided by the molecular weight, that is 94.5 gram, and uh, divided by the volume, and that is nothing but what? 500. When you write in liter, it will become like this. So when you simplify all this, you are going to get alpha approximately equal to 0.34, but they are asking percentage dissociation. That means alpha multiplied by 100, and this will be equal to almost 34%. Next is a factual question from solid state, very straightforward. Imagine the room you're sitting in as a cube, and then we can arrive at the answer. Here the answer is straightforward, and that is 8, right? In a BCC, the coordination number is 8. Among the following, how many compounds are amphoteric? Now, this is a very popular question. All the amphoteric oxides that's present in your course has to be by hearted. So here, compounds of beryllium or oxides and hydroxides of beryllium are amphoteric. So that is the key thing. These two are strong bases. Next question is to evaluate molarity, which is very simple. Moles by volume in liter of the solution. So what is moles? We have 4.5 gram is the given mass. Molecular mass is 90. What is the volume? 250 in ml. We put it in liter, we get this. So now what I have, if I simplify So it's like 2 here, and this 2 gone, 50 here, 50 gone, 5 here. 1 by 5 is 0.2. So 0.2 is the molarity. Next one is the question from atomic structure. They are giving a relationship between the mass of lithium plus 3 ion and proton. Let's consider a full stop here. So this is given to you, and they are saying that they are accelerated by the same potential difference, and they are asking the ratio of de Broglie's wavelength. Now, de Broglie wavelength is related something like this, right? Not something like this, exactly like this. So if I'm going to simplify this particular part, this is 2 mke will fit in here. And again, if I go ahead, kinetic energy can be written as charge multiplied by the potential difference. So when I take the ratio, the constants will fly off. Only thing that will depend is on mass and the charge. So lambda of lithium plus 3 divided by lambda of proton will be equal to, I'm flying off or flagging off or cancelling this constants. What is remaining in the equation, I'm keeping that. So proton things will come up. The charge of proton is E, and the mass is, say, for example, m times of proton divided by the charge of the Li plus 3, that is 3 times of E, and mass, they are giving 8.33 times of mass of proton. If I cancel them up, I'm getting 1 upon 8.33 times 3 will roughly end up being 125, and out of the root it will become 5. So 5 means here 0.2, it's 0.2, which can be written as 2 into 10 to the power minus 1. So definitely x is equal to 2. So that's the end of the paper discussion. All the best for the rest of the upcoming exams. Thank you very much.